7 miles above your head right now, there is a river of air moving faster than any storm system could ever move on the ground below it. And this year, that river has been doing something meteorologists do not see very often, breaking down in two completely different ways within the same 12 months. When forecasters say the jet stream just broke, they are not reaching for a dramatic headline. They are describing a genuine shift in the exact mechanism that decides whether the UK gets floods, drought, storms, or record heat. And in 2026, that mechanism has misbehaved almost every single month it has had the chance to. Stick around, because understanding what actually happened up there explains almost everything that has gone wrong down here this year. If explanations like this are useful to you, get subscribed now, because this pattern is not finished yet. To understand what broke, you first need to understand what the jet stream normally does. Picture a fast-moving current of air roughly 5 to 9 miles above the ground, flowing generally west to east across the planet, powered by the temperature difference between cold polar air to the north and warmer air further south. Under normal, healthy conditions, that current stays relatively straight and stable, acting almost like a fence line that keeps Arctic air locked up where it belongs while steering Atlantic storm systems along a fairly predictable, orderly path toward Europe. When meteorologists talk about the jet stream breaking down, they are usually describing one of two things going wrong with that fence. Either it becomes unusually wavy, developing large, slow-moving loops that dip much further south or swing much further north than it should, or it splits entirely into two separate branches, a phenomenon called split flow, where one stream curves toward the pole and another dives toward the subtropics, with nothing left steering weather along a single predictable track anymore. Both versions share the same underlying consequence. Instead of weather systems moving through in a normal, orderly sequence, they get stuck in place, amplified in strength, or shoved somewhere they would not normally go. This year, the UK experienced both versions back-to-back within the same 12-month stretch, which is a large part of why this particular story has drawn so much attention from meteorologists. January opened with an unusually strong and unusually southerly jet stream locked in place over the Atlantic, dragging one low-pressure system after another directly toward the UK with barely any recovery time between them. According to the Met Office's own analysis at the time, that southward shift traced back to repeated clashes between freezing Arctic air and much warmer air over North America. A sharp temperature contrast that acts like fuel, energizing and strengthening the jet stream well beyond its usual winter intensity. The result was a genuinely remarkable month. Cornwall and County Down both recorded their wettest January on record. Northern Ireland logged its wettest January in 149 years, and across the UK as a whole, 26 individual weather stations set brand new monthly rainfall records, some of which had stood since the 1960s, broken in a matter of weeks rather than decades. Then within a few months, the picture flipped almost completely. By late spring and into early summer, a very different kind of jet stream disruption took hold. One meteorologist described using an entirely different vocabulary: blocking. A blocking pattern happens when a large, stubborn area of high pressure effectively parks itself in place and refuses to move physically, obstructing the jet stream's normal path and forcing it to divert dramatically around the obstruction, sometimes for weeks at a stretch. This year, that block set up repeatedly, either directly over the UK or just to its north, and the consequences were almost the exact opposite of January's relentless storm parade. Instead of a fast-moving jet stream dragging one Atlantic low after another across the country, a weakened, displaced jet stream let high pressure dominate for extended stretches, producing exactly the kind of prolonged, stagnant heat that defined this year's extraordinary run of temperature records. The UK's first heat wave of the year arrived in late May, when the record for the hottest May day was broken twice within 24 hours, eventually reaching just over 35 degrees Celsius at Kew Gardens in London, smashing a record that had stood since 1922. A second, more intense heat wave followed in June, when the country's all-time June temperature record was broken outright, with readings pushing close to 38 degrees Celsius in Norfolk, among the hottest days ever recorded anywhere in the UK. By the time a third heat wave arrived in early July, Britain had already logged a record 8 individual days above 34 degrees Celsius in a single year, beating a mark that had stood jointly since 1976 and 2020, and 2026 had become the first year in the entire UK weather record to see temperatures reach 35 degrees or higher in May, June, and July, all within the same 12 months. Both of these outcomes, the relentless winter storm parade and the record-breaking summer heat, trace back to the same underlying cause, even though they produced almost opposite weather. A weaker, more erratic jet stream, whether it is meandering south to drag in repeated Atlantic storms, or getting physically blocked in place by a stubborn ridge of high pressure, is now widely understood by climate scientists as one of the clearer atmospheric fingerprints of a warming world. Here is the mechanism researchers point to most often. The jet stream is powered by the temperature contrast between the cold Arctic and the warmer air further south. But the Arctic has been warming significantly faster than the rest of the planet, a phenomenon known as Arctic amplification. As that temperature gap between the pole and the mid-latitudes narrows, the jet stream loses some of the driving force that normally keeps it fast, tight, and relatively straight. A weaker jet stream tends to become wavier and more prone to getting stuck in place, whether that is stuck, delivering storm after storm along an unusually southern path, or stuck, allowing a heat-trapping ridge of high pressure to sit motionless for weeks on end. That distinction, a weakened driving force rather than a stronger one, is actually the opposite of what a lot of people assume when they picture extreme weather being linked to a more dangerous, more energetic atmosphere. In this case, it is closer to the reverse. A jet stream with less energy pushing it along tends to wander more and get trapped more easily, producing longer, more persistent spells of whatever weather happens to be sitting underneath it at the time, whether that is storm after storm in January or heat wave after heat wave in June and July. There's an additional layer of complexity worth understanding here too, one that goes beyond Arctic amplification alone. Ocean temperature patterns thousands of miles away can also nudge the jet stream into unusual configurations, and this year, sea surface temperatures in the tropical Pacific have been closely watched for exactly this reason, with a strengthening El Niño pattern developing through the middle of the year, when those waters run warmer in the pattern. Associated with El Niño conditions, it tends to encourage the kind of split flow described earlier, where the jet stream effectively divides into two separate branches, a stronger, more southerly subtropical branch, and a northern polar branch pushed further toward the Arctic than usual. That kind of split does not just affect one country in isolation. It reshapes storm tracks and temperature patterns across an entire hemisphere simultaneously, which helps explain why so many different regions have reported unusually erratic jet stream behavior within the same stretch of months. Public health and climate researchers commenting on this year's remarkable clustering of extremes have made a point of stressing that the slow creep of average summer temperatures over time matters less, from a practical standpoint, than the increasing frequency and intensity of extreme events themselves, extremes that compound and stack on top of each other in ways that infrastructure, agriculture, and health systems built for a cooler, more stable climate were never really designed to handle. 3 separate heat waves before the middle of July is not simply an unlucky coincidence layered. On to an otherwise normal year. Estimates following the May heat wave alone attributed hundreds of excess deaths to that single event, and health authorities issued repeated amber and red heat alerts as the pattern repeated itself through June and into July. It is what a weaker, more erratic jet stream tends to produce once it settles into a blocking pattern and simply refuses to budge. There is a genuinely strange irony sitting at the center of all this, too. The same broken jet stream mechanism that trapped the UK under a relentless run of Atlantic storms in January is mechanically related to the one that trapped the country under a motionless heat dome in June and July. Both are symptoms of the same weakened, wavier jet stream, just expressing themselves in opposite ways depending on which direction the resulting loop happened to bend and where the resulting blocking high-pressure system happened to settle. It is worth understanding, too, how forecasters actually track something as invisible as a river of air several miles above the ground, because it is not guesswork. Weather balloons launch twice daily from stations around the world, satellite measurements of temperature and pressure at different altitudes, and aircraft-mounted sensors all feed continuous data into the same supercomputer models used to predict storms and heat waves days in advance. Meteorologists specifically watch the jet stream's position, its speed, and how wavy or straight its path looks on any given day, because a jet stream running fast and relatively flat tends to mean quick moving. Changeable weather passing through efficiently, while a slow, deeply looping jet stream is the clearest early warning sign that whatever pattern currently sits beneath it, stormy or scorching, is likely to stick around far longer than anyone would prefer. That is also why long-range seasonal forecasting remains so notoriously difficult, even for the world's most sophisticated models. Predicting exactly when and where the jet stream will buckle into a loop, split into 2 branches, or get physically blocked by a stubborn area of high pressure involves an enormous number of interacting variables. Arctic temperatures, ocean patterns thousands of miles away, soil moisture, and even conditions in the stratosphere above the jet stream itself. Confidence tends to stay relatively low until a pattern is only a week or 2 away from actually arriving, which is precisely why forecasters were still debating, deep into last winter, whether 2026 would end up being defined by storms, heat, or both. As it turned out, it delivered both extremes within the same year, almost as if to make the underlying point as clearly as possible. So what does a broken jet stream actually mean going forward, beyond simply explaining why this particular year has felt so relentless? It means the old assumption that extreme weather arrives, eases, and then gives way to a return toward average conditions, is becoming steadily less reliable. A weaker, more easily blocked jet stream does not just produce occasional extreme days, it produces extreme spells, storms that queue up one after another without normal breathing room, or heat waves that refuse to break for weeks at a time, because the very system that used to reliably move weather along has lost some of the energy that once kept it doing so. For a country like the UK, built around infrastructure, agriculture, and public health systems calibrated to a narrower, more predictable range of weather, that shift matters enormously. Reservoirs designed around historical rainfall patterns, railways engineered for a specific temperature corridor, flood defenses built using decades-old rainfall records. Records that, as this year has repeatedly shown, are now getting broken within a single afternoon, rather than standing untouched for another 60 years. None of this is entirely without precedent, which is actually part of what makes this year so revealing. The UK has seen jet stream-driven extremes before. The winter of 2013 into 2014 brought a similarly relentless run of Atlantic storms tied to an unusually active, southward displaced jet stream, flooding large parts of southern England for weeks on end. The summer of 2018 brought a stubborn blocking high that parked itself over the UK for much of June and July, producing one of the driest, hottest summers in decades, and turning parks and hillsides across the country brown almost overnight. What sets 2026 apart is not that either individual event was unprecedented on its own. It is that both extremes, the flood-driving southerly jet and the heat-trapping block, showed up in force within the same calendar year, back to back, rather than years or even decades apart the way they traditionally have. Climate scientists studying long-term jet stream behavior have been warning for years that this kind of compressed timeline, extreme wet followed, quickly by extreme dry and hot, is exactly the pattern a warming Arctic and a weakening temperature gradient would be expected to produce more often. 2026 is the clearest single year of evidence for that warning that the UK has seen so far. There are real, practical consequences to this shift that go beyond simply having an unusually eventful year of headlines. Insurance industry analysts have already flagged the compounding cost of a wet winter followed by a scorching summer within the same 12 months, since flood damage, claims from January, and heat-related infrastructure failures from June and July land on the same annual balance sheets, rather than being spread across separate, more manageable years. Water companies that spent the early part of the year managing overwhelmed reservoirs and flood defenses found themselves just months later issuing hosepipe bans and drought warnings as the same reservoirs ran low under weeks of blocking heat. Rail operators dealing with flooded lines in January faced heat-related speed restrictions on the exact same stretches of track by June, as rails expanded in temperatures they were never originally engineered to handle for this many consecutive days. None of these systems were built with the expectation that a single year could deliver record-breaking extremes at both ends of the spectrum. They were built for a climate that assumed a wet winter and a hot summer would balance each other out over time, not stacked directly on top of one another within the same 12 months. Because the jet stream is quietly behind more of this year's biggest weather stories than most people realize, from the record floods in January to the record heat that followed it barely 5 months later. And if this finally helped the science click into place for you, tap that like button before you go. It genuinely helps more people find explanations like this instead of just the headlines.